Alright, subscribers, welcome back to another episode of Science with Zerbeck. Today, what we're going to be talking about is section 16.6 in AP Chemistry. So, before we get going with this lesson, I'm going to outline a couple of objectives that I want you to be able to accomplish by the end of this video. So, objective number 1, calculate the pH for a weak acid solution in water given the acid concentration of Ka. Calculate Ka given the acid concentration and pH. And then the second objective is calculate the percent ionization for an acid knowing its concentration in solution and the value of Ka. So let's get started with just a generic definition of what a weak acid is. So a weak acid, all a weak acid is a substance that only partially ionize in a aqueous solution, and that is an acidic substance there. So let me write that down, and then we'll talk more about it. All right, so there is that written definition. Just a couple things out of this. Number one, this is an acidic substance. So for us, at least right now, we're going to say that it's going to donates some H pluses in solution, but only partially. In a strong acid, we saw that 100% of those H pluses broke off of a strong acid. So if we move on to a generic equation, this, in my mind, helps me differentiate between strong and weak acids. So right here, we'll just have a generic weak acid equation. And so in a generic weak acid equation, what we have is this. We're going to call our acid, our weak acid, HA. And this is going to be dissolved in water, so it's an aqueous solution. And again, we have to show that it is dissolved in liquid water. And so something different here, because it's only partially ionized, this right here, this doesn't get that one reaction arrow. This substance right here, a weak acid, actually comes to equilibrium. So with our equilibrium, what happens is this. The H gets donated to the H2O, and that becomes that hydronium. And then over here, you get that conjugate base to form as well. Now, one thing unique about this, because we are a weak acid, and really because we're at equilibrium, we can write an equilibrium constant expression. So for this, remember, equilibrium constant expression is products over reactants. So what we are going to do is this. We're going to say our K for our acid. So we're going to call this is going to be Ka equal to our products, which is H3O plus, times our conjugate base, all divided by just our weak acid. Now we don't include water because it is a liquid substance. Only aqueous and gas substance appear in that equilibrium constant expression. From here on, we're typically just going to be dealing with aqueous solutions too. So it has to be aqueous to be into this Ka. Now, we get down here with what is Ka. So Ka is known as the acid dissociation constant. So let me pause and write that down. All right, so again, Ka is an acid dissociation constant. And these values can be looked up. There's charts, and there's charts actually in the back of your textbooks that show the exact Ka value for a particular weak acid. Now, there are two types, or two generic types of Ka. So I'm going to put two types, and the first generic type is a large Ka. Now, what a large Ka means is this: a stronger acid. What that means with a large Ka, we are going to have something that, I shouldn't say almost always dissociates, but it's going to dissociate very, very much. Now, the other side, or the flip side, is a small Ka. And when I say small, I mean like times 10 to the negative 10th, or times 10 to the negative 12th. Something really, really small with a lot of zeros in front of it. This means a weaker acid, and it means less of that substance will dissociate in an aqueous solution. Now, that's great that we have a generic understanding of what a weak acid is. Now we need to put our knowledge to the test and be able to do some calculations for our Ka. So we have a weak acid, formic acid right here. Formic acid is a weak acid, and it's found to have a pH of 2.38 at 25 degrees Celsius. Remember, we have to worry about temperature because we're dealing with K. And we want to know the actual Ka for formic acid at this temperature. So from here on, the first step in everything that we do here is to give ourselves an equation for this weak acid, or for any acid or base problem. So we start out here, and we're going to need most of the paper here. We start out here with the formula of formic acid, and it's aqueous, so that means it is dissolved in water, and it comes to equilibrium because of this. One, it is not one of the 7 strong acids. And 2, we're dealing with Ka, so that should indicate 2 things. Hey, I have a weak acid. Now, this comes to equilibrium, and we get our hydronium. We get our hydronium concentration to be H3O plus, and then we get just our formate ion, which is HCO minus, and that is aqueous. Now what we have to bring back is our ice chart. And I squeezed some room here. I wish I would have left a little bit more room, but we have our ice chart. Now, initially it said we had a 0.1 molar solution of formic acid. So what we do is we put 0.1 molar, and we're allowed to put molar there, 0.1 molar solution of formic acid. Now, initially this is 0 of our hydronium or our formate ions. Now, H2O, because it's not going to be in our Ka, we don't need to worry about it. You can just leave that alone, and actually an X is not a very good term. Let's use just a dash mark, all right? So we don't need to worry about H2O. Now we have to think about this change. Well, we are given the pH of this formic acid to be about 2.38. Well, let's go back. Let's remember what the formula for pH is. And pH equals negative log of our H plus, or we can call this H3O plus. And so we have the pH to be 2.38 equals negative log of our of our H plus? Well, if you remember, we took both sides by -1, so we end up with -2.38 equals our log of our H plus. Now, to get rid of or to have the H plus by itself, which is what we want to find the hydronium equilibrium concentration, we have to take the inverse of the log of both sides. So I'm going to grab my calculator here, and I am going to take the inverse of -2.38. Now, I had 3 digits, so I'm going to round my calculation to 4.17 times 10 to the -3rd. So this equals our H plus, which can also be exchanged for our hydronium ion concentration. So at equilibrium, remember the pH has to be calculated at equilibrium. Once this substance came to equilibrium, what we get is this. We get a hydronium calculation of 4.17 times 10 to the -3rd molar. Now we went from 0 to this value here, so that means we gain 4.17 times 10 to the -3rd. Again, we do a little bit of stoichiometry here, and so this right here is a 1-to-1 ratio. So if we gained 4.187 times 10 to the -3rd, that also means for our formate ion, we gained 4.17 times 10 to the -3rd molar. And that gave us an equilibrium value of 4.17 times 10 to the -3rd molar. All right, so we have 2 of the 3 things we need to find our Ka. Now we need to worry about our value here for formic acid. Now, if we gain 4.17 times 10 to the -3rd because we had a 1-to-1 ratio, that means over here we are going to lose the same amount, and that's all because of the 1-to-1 stoichiometric ratio. So we lose 4.17 times 10 to the -3rd molar. So what we need to do here is this. We need to take 0.1 and we need to subtract it from 4.17 times 10 to the -3rd. Now, the answer that I get, I'm going to take it out of scientific notation, is 0.0958. So at equilibrium, there is 0.0958 molar of our formic acid. Now what we can do is we can finally plug this into our Ka expression. And so to calculate Ka, I'm just going to give the generic, in this case is going to be equal to our H3O plus concentration times our formate ion, which is HCOO minus concentration, all divided by our formic acid concentration at equilibrium. So now, if we plug some values into our equation here, H3O plus was found to be 4.17 times 10 to the -3rd at equilibrium. So we end up with, and I'm going to write small, 4.17 times 10 to the -3rd times the equilibrium concentration of formate, which was 4.17 times 10 to the -3rd. So again, I'm going to write fairly small. And then on bottom, we need the concentration of formic acid. So we end up with the value we calculated, 0.0958. And before I go through this calculation, a couple things that I want you to notice. One, there was not much of this formic acid used to form either of these particular substances. So, not much of this formic acid was actually ionized. Now, through our calculations here, what we are going to do, I'm going to put a double set of parentheses, and I'm going to put 4.17 times 10 to the negative third, and I'm going to multiply that by 4.17 times 10 to the negative third. I'm going to close my double set of parentheses. Now, that's just the top portion. I need to divide it by 0.0958. And when I get that, my Ka value of formic acid to 3 total digits, Ka is 1.82 times 10 to the negative fourth. Now, remember K is at a specific temperature, which it's at 25 degrees Celsius. So that's how we calculate our Ka when we know all of these things, or when we are able to calculate our equilibrium concentration. All right, so going through this, we need to talk a little bit more about, hey, well, what makes a weak acid a weak acid? So as we go through this, what we first need to look at, what we first need to concentrate on to figure out a little bit more of why this particular thing, why it counts as a weak acid, we have to look at this value called percent ionization. And so percent ionization is just simply defined as how much of a substance, a weak acid substance, dissociates its H+. Particularly, it's defined as the measure of the strength of an acid through the amount of acid that dissociates. So let me write that down, and then we'll talk about a formula here in just a second. All right, so kind of a wordy definition here. Simply put, and I like simple here, we can just put this into a formula. And so our formula is going to be percent ionization is equal to the H plus that dissociates divided by the original acid concentration. All right, this is all going to be multiplied by 100, and the easiest way to see that is through an example. So we have a 0.1 molar solution of formic acid, the stuff we just dealt with, and in this particular example, it is going to contain, very similar to what we had, 4.2 times 10 to the negative third molar H+. We want to calculate the percentage of the acid that is ionized. So all we need to do in our formula, I'm going to write this out, percent ionization is equal, in this case, to our H plus that dissociates, all divided by our original concentration of our acid. And then don't forget to multiply by 100 because we are dealing with percent. Now, percent ionization, I'm going to call it percent I there. Our H plus that dissociates is this value given as 4.2 times 10 to the negative third, all divided by the original concentration, which was 0.1. And then, as always, don't forget to multiply by 100. So what we are going to do here is we are going to take 4.2 times 10 to the negative third, and we are going to divide it by 0.1. We press enter, and we have to remember to multiply by 100. Now, I'm going to take it out of scientific notation there, and our answer gives us 4.2. So our percent ionization for this particular problem is 4.2% ionized. Now, typically, and I want to make this side note here, this is a generic statement, number one, but typically a weak acid has a percent ionization of less than 5%. So let me make that here. A weak acid has a percent ionization of less than 5%. Now, this isn't always the case, but typically it is. Typically, you won't see a weak acid much more ionized than 5%. So you can tell the big difference here between a weak and a strong base, or weak and a strong acid, excuse me. And another thing is there's not much middle ground here. You're either a weak acid ionizing less than 5%, or you're one of those 7 strong acids that ionize completely. So, as we go through this, going through a couple more examples, and this is the best part about our values here for acids and bases, is going through these calculations. Now, it will take a little bit longer, so I'm just warning you right now. We want to know what is the pH of this 0.2 molar solution of HCN. So the first thing that we always do is say, is HCN one of those 7 strong acids? The answer is no. It's not on that list of 7 that we've gone over before. So HCN is going to be a weak acid. So the first thing that we need to do is we need to say HCN is a weak acid. It gets combined with water, H2O, and it's weak. It's a weak acid, so it goes to equilibrium. Now, at equilibrium, or on the other side here, we get H3O plus, and we get our cyanate ion. Now, just like we did on the previous problem, this is going to have an ice chart. Okay, so our initial value of HCN is given at 0.20 molar. So we're given 0.20 molar. And we don't need to worry about water. I always put a line just so I don't confuse myself. And then H3O. Initially, we're at 0 H3O. Same thing with cyanide. Before this equilibrium, or it's come to equilibrium, we're at 0 of this CN. We're at 0 of this CN ion. So now we need to worry about the change. Notice we're not given very much info in this particular problem. So our change is this. We have to lose some of this 0.2 molar HCN. So we're going to say minus X. And then on the flip side, we have to gain some H3O. So we say plus X. And then our cyanide, we have to gain some of that as well. So we say plus X. And I just have one X because of those stoichiometric calculations. Remember, the coefficient becomes down in front here. So if you ever have to deal with that, remember coefficient does play a role into it. Now what we get into is our equilibrium values. And so we're left with 0.2 molar minus X. This 0 plus X is X, and then cyanide 0 plus X is also just X. Now we can concentrate on our Ka. So our Ka is going to be equal in this scenario here of our hydronium H3O plus times our Cn minus, all divided by that original concentration of HCN, or excuse me, the concentration at equilibrium. Now all we got to do is plug some numbers in. And I'm going to leave a little space for Ka because we're going to get to that in just a second. So give yourself a little space for Ka. We get to this. H3O plus is an X times the concentration of cyanide, which is also an X, all divided by the equilibrium concentration of HCN, which is 0.20 minus X, and I'm going to get rid of the M so we're not confused. And then we have this business about Ka. So Ka, couple different places that you can find Ka. The best portion of this book is right here. I'm going to shift this away for a second. Is right here. So this right here is in page 1062 of your book. It's actually appendix D. It says aqueous equilibrium constants, and that's what we want. We are dealing with HCN. So on this hydrocyanaic acid, if you find this, and it's not very big here. Maybe I'll zoom in a little bit. Oh, perfect. HCN. If we scroll over, HCN has a value of Ka of 4.9 times 10 to the negative 10th. So what we're going to do there is we're going to write that value down, 4.9 times 10 to the negative 10th, right there, right onto our value for Ka. So again, 4.9 times 10 to the negative 10th. All right, so that's how we look that up, and now we can use it. Now we can use it in our calculations. Let me zoom out here. Oop, went a little far. Perfect. All right, so if we go through this process, I don't know if you can forecast it out, but we're going to have an x squared, and we are going to have an x. What this means is that we are going to have to use the quadratic if we go about it how we have it set up here. Now, remember from the last problem, this subtraction here was really, really, really small. So what we can do to avoid quadratic, we can make an assumption. So our assumption is this. We are going to assume, always write down your assumptions. Always write this down. We are going to assume this. If our Ka times 100 is less than our original concentration of our acid, and I'm talking much less, all right, then we assume that this minus x is irrelevant. And maybe I'll save that here. Let's go through this. So 4.9 times 10 to the negative 10th times 100. That's the first thing that we are going to do. We have to have 4.9 times 10 to the negative 10th times 100. We have to have this much, much less, and it's just 4.9 times 10 to the negative 8th. We have to have it much, much less than our original concentration. So our original concentration is this, 0.2 of our acid. Now, ask yourself, is 4.9 times 10 to the negative 8th much less than 0.2? The answer is yes. The answer is yes. So what we can do is this. We can assume that 0.2 minus x is roughly equal to just 0.2. And that's because our assumption here, or our loss of x, is going to be so small, this is not going to make a difference. So what we're going to do, I'm going to rewrite this with our assumption. So 4.9 times 10 to the negative 10th equals x squared divided by, here's our assumption, divided by 0.2. So what we end up doing here is this. We end up doing this. We have 4.9 times 10 to the negative 10th. We cross multiply it by 0.2. And so we're left with 9.8 times 10 to the negative 11th equals x squared. We get rid of x squared by taking the square root of each side. So we take the square root. I second put my answer that I just had in there. And I get a value of x to be, I'm going to round it, 9.9 times 10 to the negative 6. So x equals 9.9 times 10 to the negative 6. Now, if you remember back here, we want to calculate the pH. Well, x right here is equal to the concentration of H3O plus. So what we can do now with this 9.9 times 10 to the negative 6 is we can plug it back into our equilibrium expression, or not our equilibrium expression, our pH formula. And so our pH that we get is negative log of this value right here. So it's negative log of 9.9 times 10 to the negative 6. And so I plug this into my calculator. Negative log times 9.9 times 10 to the negative 6. And I press enter. And I get a pH, a perfect pH right here, of 5.0. So our pH is equal to 5.0. Now, this makes sense here that our pH is still an acid, but it's a relatively weaker acid here. So, again, we can avoid, what's really nice about acids and bases, if this assumption checks out, we can avoid the quadratic formula. Now, let's keep moving on. Let's go a little bit more complicated, and let's go to this. Something called a polyprotic acid. Now, a polyprotic acid is still going to be a weak acid, but it can donate our H, or it can have multiple H's to donate. Specifically, the definition here is this. A polyprotic acid is defined as an acid with more than one ionizable proton. So let me write that down, and then we'll talk about it. All right, so there is that definition here. And to see this in actual action here, let's go through an actual example of something that's a polyprotic acid. And this example right here, we're going to use it just in this next equation, or this next example, is sulfuric acid, which is H2SO3. So notice this. There are two H's, and both of these H's can be donated, which makes both substances an acid that can donate its proton. And so our first donation here, or our first type of acid-base reaction, is H2SO3, which is aqueous. Now, H2SO3, sulfuric acid, is not a strong acid. It reacts with water, and we come to equilibrium because because we are a weak acid, and we end up with H3O plus, and we end up with our HSO3 1 minus. Now, what we can do is this, and I'm running out of room here, so what I'm going to do is the Ka for this first one is 1.7 times 10 to the negative second, and again, there is no unit on Ka there, and so it's 1.7 times 10 to the negative 7th. Now, that is a pretty highly ionizable substance. Now what we can do, the second step here, is we're going to start out with this HSO3 1 minus. So we get HSO3 1 minus, and we put it in solution. Again, it reacts with water. It's still weak, and so it comes to equilibrium as H3O plus now SO3 2 minus. And now what we have here is the second H broke off and acted like an acid. Now again, I'm running out of room here, and so our Ka for this second part here is equal to 6.4 times 10 to the negative 8th. So a couple of things. Notice how much bigger this first Ka is as this second Ka, or compared to the second Ka. So as you lose progressive H's of a polyprotic acid, it's going to get weaker and weaker and weaker. So let's go ahead. Let's use this example here as we go through our next, actually it'll be 2 pages worth of an example. So we want to know, what is the pH of a 0.45 molar solution of H2SO3? So we start out with H2SO3, and it's aqueous. It gets dropped in water there, and it forms, it goes to equilibrium, right? It goes to this H3O plus, it goes HSO3 1 minus, and this is aqueous there. So what we get into is this. We need to, because it's a weak acid, we need to set up our ice chart. So initially we have 0.45 molar. We don't need to worry about water, and initially there's no hydronium and there's no HSO3. We then need to worry about the change. All right, so coefficient, we lose some amount X. Don't need to worry about water. We gain some amount X. Again, one coefficient, and we gain some amount of HSO3. So at equilibrium, we end up with 0.45 minus X, X from H3O, and X from HSO3. Now, our Ka, I always like to put our generic example here. Ka is going to equal, in this case, our concentration of H3O plus times our HSO3 1 minus, all divided by our equilibrium concentration of H2SO3. Now, what I'm going to do out to the right here is this. Our Ka, remember from our first example, this Ka, which can be looked up in your book, is 1.7 times 10 to the negative second. So I'm going to insert 1.7 times 10 to the negative second. And this is going to be equal to our concentration of equilibrium of H3O, which is X, times our concentration of HSO3, which is still X, all divided by 0.45 minus X, which is that equilibrium concentration for H2SO3. Now, this business is messy, right? So we're going to see if our assumption holds true. If not, we got to do a little bit of work with our quadratic formula. So always write down your assumptions. We want our Ka, which is 1.7 times 10 to the negative second times 100 to be less than our original value for our acid. We want it to be less than 0.45. So we do this. We say, hey, 1.7 times 10 to the negative second times 100 is this 1.7. So 1.7 is less than 0.45. This is not true. Okay, so we cannot use our assumption, and I know this stinks. So what we are going to do is this. We are going to have to use the quadratic formula. And so to save a little bit of time here, to save a little bit of confusion, what I'm going to do, I'm going to pause the video, and then I'm going to write out our value for our quadratic and also calculate it. I know you probably have experience with the quadratic, and you can probably do this on your own. But again, to save some time in the video, to go through it, I'm going to calculate the x's with that quadratic formula. All right, so here is the quadratic equation. Again, we had to use it because this assumption did not hold true. So after doing this, I get two values for x. I get 0.079 for 1x, or I get negative 0.096. Now, if you look here, this is the value for x. I cannot have, in this scenario, a negative value for x. So that means x has to be 0.079. And remember, this is the H3O plus concentration. So that means our pH is negative log of this value here of 0.079. So if we plug that into our calculator, here, we get negative log of 0.079. We press enter, and we get a pH of 1.10. So our pH here is 1.10. And yes, this may seem like a strong acid, but look how big our Ka was. So yes, this is a weak acid, but it ionizes a lot. It ionizes a lot of these H's in this first setup here. Now, going through this second problem, we're going to use some values here that we started out with. We want to know, at the end of the day, what is the equilibrium concentration of the SO3 2- ion in a solution of H2SO3. So what we have is a continuation of what we just did. We're going to pick off exactly where we left off. We had HSO3 1-, which is an aqueous solution. It's going to be an acid, so it's going to be placed in there with water, and it's going to come to equilibrium. We get, at equilibrium, H3O plus, and we get as well our SO3 2-. Now, our ice chart here, we don't have a whole lot to work with besides this 0.45, which isn't really helpful. So from that previous page, remember the value of HSO3, which was also equal to X, and this is from previous calculations, was 0.079. 0.79 molar. Now we don't need to worry about water. Initially here, there is some H3O plus, and that H3O plus is also 0.079 molar. And that's because, hey, we had some H plus in that solution. So both of these things came from that previous problem that we did. Now, initially though, there is no SO3 2 minus. Now, when this H plus breaks off, we're going to lose some of that value there. So we're going to say minus X. We're going to gain some more value for our H3O plus, and we're going to gain some value here for our SO3 2 minus, or our sulfite ion. So at equilibrium, we end up with 0.079 minus X. I'm even mistaking myself here. We have 0.079 molar plus X, and then X just for SO3 2 minus. Now, I always like to do this, but Ka equals what we have at equilibrium. So we have H3O plus, we have our SO3 2 minus, and then at equilibrium we have HSO3 as our 1 minus. This right here, we have to enter our Ka, which from the previous page, I'm just reading off, our Ka is 6.4 times 10 to the negative 8th. This is equal to our value of H3O plus, which we're going to squeeze some stuff in here, 0.79 plus X times our X, all divided by 0.079 minus X. Now, we want to use this assumption. Let's see if this assumption will hold true. So our assumption here, our Ka, which is 6.4, our 6.4 times 10 to the negative 8th, has to be multiplied by 100, and it has to be less than our original concentration of HSO3, 0.079. So if we plug this into our calculator here, I'm going to take 6.4 times 10 to the negative 8th times 100, and I get this value here, 6.4 times 10 to the negative 6. So 6.4 times 10 to the negative 6 is much less than 0.079. So this is true. We can actually make two assumptions here, and that's because we have a plus and minus X. So we can assume 0.079 minus X is close enough, or if X is too small. So we just end up with 0.079, and then 0.079 plus X, same assumption. We can just assume that, hey, that is virtually 0.079. So then, what we can do, we can say 6.4 times 10 to the negative 8th is equal to not 0.079 plus X, but just 0.079 times our X, all divided by 0.079 X. So as you can see, these values will cancel out, and so our X, our equilibrium concentration here, is this. Our X is just going to be equal to our Ka. So X will equal 6.4 times 10 to the negative 8th, and so that means the concentration of SO3 2 minus is just equal to 6.4 times 10 to the negative 8th molar. All right, so This has been a lengthy video. There's a lot of acid-base chemistry going on here. I hope you've enjoyed some of this. I hope you have learned some things here. And so if you have, don't be afraid to like this video, and never forget to keep subscribing.